Good morning. Today we learn about properties of DFT. So I think in the last class we have studied about what DFT is, some of its applications, its advantages and all. Okay, that is DFT is nothing but discrete Fourier transform. So I give special importance to this. Why? Because in your syllabus this DFT is given more importance. Why? There are two topics in your syllabus. One is definition of DFT and the other is properties of DFT. So a definition and all we have studied in task class. Now today we will learn about properties. Now here I present before you nearly 17 properties of DFT. So this is just because in your syllabus this topic is given more importance. That's why I am giving here nearly 17 properties. So depending upon the weightage of questions, you can write. If it is tasked like an essay question, you can write all these 17 properties. Or if it is the question is of low weightage, then you can write accordingly. Okay. So anyway, try to study this. Proof and all is not necessary. Those who are interested in learning the proofs can go through the reference books that is given in your syllabus, or else you can go to Google Books and search for the same. Okay. Now here I have collected a few 17 properties from several books and it is presented before you. So let's begin the session. This is the properties. The first property is periodicity. Suppose that you have got two DFT sequences, that is x of n and x of k, and here the termed as DFT pair. Then x of n plus capital N is equal to x of n for all n. Then capital X of k plus n is equal to x of k for all k. Here x of n and x of k are DFT pairs and the capital N is actually the length of the sequence. Next is linearity. If DFT of x of n is equal to x of k and DFT of y of n is equal to y of k, then DFT of a variable, say a, x of n plus another variable, say b, y of n is equal to a x of k plus y plus b y of k, which we have already learned in simple mathematics. Then next is about circular convolution. Suppose that you have got three sequences of length n, that is they are x1n, x2n and x3n. Then if you take inverse transform of the DFT product of x1k and x2k, then we obtain the circular convolution as x3n is equal to 1 by n summation over k equal to 0 to n minus 1 x1k x2k e raised to 2 pi nk by n, where n range is less than or equal to 0 to n minus 1. Then substituting the inverse transform of x1k and x2k, we obtain another relation, that is x3 instead of n we are writing m. Since we are applying inverse transform, then it will be summation over n equal to 0 to capital N minus 1 x1n x2 of m minus n capital N, where m within less than or equal to 0 to n minus 1. So here capital N stands for length of the sequence. x1k is the DFT of the sequence x1n and x2k is the DFT of the sequence x2n. So just explain the terms, no need of writing the proof, just explain what each term stands for and the statement. That's enough. Next is time reversal. If DFT of x of n is equal to x of k, then DFT of x of minus n equal to capital X of n minus k. There is no need of writing these steps. Just write if DFT of x of n equal to x of k, then DFT of x of minus n negative, so shows time reversal of n equal to x of n minus k. K within the limit 0 to n minus 1. Next is circular time shift. If DFT of x of n is equal to x of k, then DFT of x of n minus l n equal to x of k e raised to minus j 2 pi k l by n. So here L is the shift applied. Next is circular time frequency shift. If DFT of x of n is equal to x of k, then DFT of x of n e raised to j 2 pi l n by n equal to x of k minus l n. So this is here L is the shift applied, or here we can denote L as time shift, and here Here L is the time shift and here L is the frequency shift. Okay. Next is complex conjugate. If DFT of x of n is equal to x of k, then DFT of complex conjugate x of n, that star stands for complex conjugate, that is equal to complex conjugate of xn minus k. Okay, so you can straight away go to this step. That is, if DFT of x of n is equal to x of k, then DFT of complex conjugate of x of n will be equal to complex conjugate x of n minus k. Next is circular correlation. If DFT of x of n equal to x of k and DFT of h of n is equal to h of k, then DFT of circular correlation is given by the expression DFT of summation over n equal to 0 to n minus 1 x of n h of n minus l n. Star is the complex conjugate equal to x of k, then h of k, star is the complex conjugate. Here, since we are speaking about the circular convolution, here you can note this n, here you can note an n here. Then in the above two cases also you can see, in these cases here there is an n and here also there is an n. That is, in circular time shift, circular frequency shift and circular correlation, you can see capital N and you can identify it as the modulo, which we have already studied in the earlier classes. Okay, so if you don't know about modulo, just go through those sessions. Next is Parseval's theorem. If it states that if DFT of x of n equal to x of k and DFT of h of n equal to h of k, then Parseval's theorem states that the summation over n equal to 0 to n minus 1 x of n h of n, that is a complex conjugate, that is again equal to 1 by n summation over k equal to 0 to n minus 1 x of k h of k complex conjugate. So here h and all we have already studied. What is h? It is actually the impulse response of the system, or the frequency response of the system. So remember, here small letter x of n is actually the discrete time sequence, whereas capital X of k is actually the DFT of x of n. Okay, now h actually stands for the frequency response of the system. Next is symmetry properties. Suppose that you have a discrete sequence x of n and its DFT is complex, then the complex form of a discrete sequence x of n is given by x of n equal to xrn plus jxin. Here r is the real part and I is the imaginary part, and small n within the limit 0 to n minus 1. And this x of n is a discrete time sequence, and whereas x of k is a DFT of x of n, and this DFT of x of n will also be in a complex form and can be written as x of rk plus jxik. R is the real part, I is the imaginary part, k within the limit 0 to n minus 1. Next, circular symmetries. Suppose that you have a discrete sequence, say x of n, and its DFT is of finite duration with n within the limit 0 to n minus 1, then that finite duration sequence is similar to that of a periodic sequence, say x of Pn equal to summation L from L equal to minus infinity to plus infinity x of n minus Ln. That is, a DFT of a finite duration sequence is similar to that of the DFT of a periodic sequence given by x of p, that p stands for periodic. Now suppose that a shift is applied, then that x of p will become x of sp, that s stands for shift and p stands for periodic. So xsp is actually the shifted periodic sequence, and that will be given by equal to x of p n minus k, or it's equal to summation from L from minus infinity to plus infinity x of n minus k minus L. Now from this we can define a new sequence which is a finite duration given by x of s n equal to xsp, that is shifted periodic sequence with n ranging from 0 to n minus 1, and it will be 0 in otherwise. So this is related to the original sequence x of n by a circular shift. So we can write the above equation in this particular form. X of s is equal to x of n minus k comma modulo n, or simply this is enough, x of n minus k capital, this n actually stands for modulo. Now So that is it. So a finite duration sequence is DFT of a finite duration sequence is equivalent to the DFT of a periodic sequence given by x of p. Now we are applying a shift to this, and on applying that shift we will get a new sequence. It is of this particular form. Okay. And then we have got another operation. There are various operations that can perform. The one is circular folding. That is, if that particular new sequence, I already told, a new sequence is obtained, if that is folded, then that particular operation is called circular folding, and that sequence will be of this particular form. Then similarly you can perform many other operations. One is circular folding, circular even, circularly odd, circularly even periodic, circularly odd periodic, conjugate even periodic, and so on. Conjugate odd periodic. Just study the expressions. Okay. So give more importance to this particular session, the circular symmetries, and these are the various type of forms. So just study one or two from this. If it is easy to study, then you can study the full part. Next is phase shifting. That is, if you have a periodic sequence with period n, that is x of m equal to xm plus ln, where l is an integer, and that l can be considered as a phase shift in the frequency domain. Or in other words, we can say that if we have a sample x of n starting from an integer say n to another integer say k, then DFT of that time shifted sample is given by this particular form. X shifted an integer m equal to e raised to j2 pi km by n x of m. Okay. Next is the symmetry property. And we know that the DFT of a discrete time sequence will be symmetric sometimes, and that is it will have um, a real part and as well as an imaginary part, and so it can also be considered as the real part can be considered as DFT even symmetric, and the imaginary part can be considered as DFT odd symmetric. So the DFT of a discrete time sequence can be sometimes complex, that is, it can have a real part and imaginary part. That real part is called DFT even symmetric, and imaginary part is called DFT odd symmetric. The figure is given below. Now the last session is circular time reversal, and the other one is circular time shift. So just compare these two and study. Here suppose that here what you do is that you have a signal. Suppose that you have a signal, and if you want to perform circular time reversal, what you do is that you first of all apply a circular extension, and then you time reverse it, and then you are picking a particular value from 0 to n minus 1. This is called circular time reversal. But in the case of circular time shift, this one, just compare, you are having a signal. Now instead of circular extension, you are applying periodic extension here. Then here you are applying time reversal, you are applying time shift. Then you are picking one value from 0 to n minus 1. Here also you are picking one value from 0 to n minus 1. This is circular time shift. The only difference is that here you are applying circular extension, here periodic extension. You are applying time shift reverse, here you are applying time shift. Then you are picking a value from 0 to n minus 1. So in first case it will be termed as circular time reversal given by this expression. In the second case it is called circular time shift, and it is given by this particular expression. Okay, so just study that expression, and while studying writing this expression, just denote what each term stands for. DFT is applying discrete Fourier transform on n length of the sequence. K is the modulus operator, which we have already learned. Okay, so write what is modulation operator and all. So just the statement, the expression, and explain what each term stands for. If there is mod here, you must write what modulus stands for or mode stands for, which I have already studied taught you in earlier classes. So you can go through. So just write these two expressions for circular shift and circular time shift and circular time reversal. Okay, next last one is circular frequency shift. Here we have got only this expression. Then about complex conjugate, there are two ways of writing the complex conjugate of a discrete sequence x of n. See here, it is x of n, the complex conjugate. This is one form, and this is another form. So these two are very much applicable, especially in circular symmetries. So just study the expression. So while writing, please remember, just write these properties according to the weightage of the questions. If it is asked like an essay question, you can write all this. Otherwise, you must write it accordingly. Here, just the statement is enough. Then the expression. When you write the expression, just explain what each term stands for. Okay. So that's all for today. Okay then. Thank you.